So the kind of idea today is that we go through some new topics and try to wrap up about convolution neural networks. And then we are going to dive into recurrent ones, which may be of interest for those of you who would like to solve differential equations and apply recurrent neural networks to that. Alternatively, if you're using recurrent neural networks for other topics, that's also a method you can consider. Now, we also have actually somebody who can help us with the project work as well, and it's Atle here. So maybe you'd like to say something about yourself, Atle. I mean, what's your background? And
I'm a PhD in Silva, and I'm a PhD in computational neuroscience. I have a background in applied physics and mathematics from NTNU, and my PhD project is on modeling and validating that model of mouse primary visual cortex. The idea is for an additional source of assistance together with Morten. I probably won't be able to help with everything, but at the very least, that could be a discussion partner and someone who can bounce ideas off of. I'm a fourth year PhD student, so I have some experience with writing papers and presenting scientific materials. I can probably give some advice on how to structure a report and so on as well.
Yeah. So the kind of idea, since my lecture session is getting close to its end, I don't think I may say something about autoencoders next week, but that will probably be the last session. But then Atle would take over and just work. We discussed the project till Anders Kvellestad begins with the Bayesian statistics and Gaussian processes part. So he plans to begin on the 28th of March. So if we look back at the schedule, just to give you this kind of information so that we are on the same kind of page, all of us, if you go back to the GitHub address of the course, there is a tentative schedule. And the kind of tentative schedule is that after today's lectures, where we would like to wrap up a little bit of CNNs and start to discuss recurrent neural networks, we may also use parts of that. I'm going to skip the generalized adversarial networks. And what Anders Kvellestad said is that he would like to begin on March 28th, just with an overview of Gaussian processes and why these are interesting. And then we have a vacation of a week. And then after that, Anders would like to continue till roughly the 10th of May. So that schedule is going to be updated. And that would lay the foundation for also the third project, if you're interested in working on Gaussian processes. But clearly, you can modify project 2 into an enlarged project 3, if that is of interest. If you wish to study, let's say, the solution of differential equations with not only deep learning methods, but also, let's say, traditional methods, and you would like to make a comparison. So there are several alternatives. By the way, can you hear me well in the back? No problems with the voice here. So the kind of idea is that March 14th will most likely be my last session, where we wrap up also the discussion of recurrent neural networks. If I get time, I may say something about autoencoders and how they can be used as ways to reduce the dimensionality, and how they can actually be also used to solve differential equations. And then I will most likely skip that. But so the March 14th and 21st, I would suggest that we also spend time on the projects, and that's where Atle also can help you. And we would just stick to the lectures hours, 12:15 to 2 o'clock, if that's okay with everybody. Does that sound okay, Atle? So we have these 2 next sessions more dedicated to actually working with a project. And then Anders is going to do a more kind of general introduction. And then after the break, we are going to simply work on Gaussian processes and Bayesian statistics. And that is going to wrap up everything. And as I said, we're also flexible with the deadlines for the projects, as long as we have everything by the beginning of June, so that we can actually grade. in due time. And that you actually get rid of all these kind of obligations, so you can focus on research, which I see everybody's nodding here. I hated taking courses as a PhD student. I just want to do research. Okay, great. So I did all my best to escape all these kind of duties. But let's bring back the Jupyter Notebook and remind ourselves a little bit about the convolutional neural networks and how we can use, let's say, an API like Keras, which follows TensorFlow, to set up a convolutional neural network. So you should feel free when you solve the projects, whether you want to write, let's say, your own neural network, and you have code examples for that, or whether you would just like to use the interface, which is provided by Keras and TensorFlow as a basic library, or if you're more familiar with PyTorch, feel free to use that. Or if you want to write, let's say, your own convolutional neural network code, I mean, you should feel free to do that as well. I normally don't recommend the latter because the code you will end up will be within this 20 credits which you have. It may be a good schematic code, but it will not be able to compete with what is provided by PyTorch and other deep learning libraries like TensorFlow. So I'm going just to switch back to the Jupyter Notebook here, and I wanted to discuss a little bit, I'll remind you a little bit about the convolutional neural network and the basic setup, which we can use with Keras. I'm just gonna sit down here so I'm not in the way here. Can you see the screen properly? Yeah, I'm not in the way here. Good. So the plans for this week is to both discuss the project and also go through recurrent neural networks, the basics. And I would probably need some time next week as well to wrap up things like long short-term memory, which is one of the ways to deal with the time dependencies. So the basics which we went through last time was how to build up a convolutional neural network with Keras. And the typical data set which we had, which we encounter again and again, is this MNIST data set. It's not so exciting. So the original data set has 28 times 28 pixels and only one color channel. And this is normally reduced to 8 times 8. And instead of 60,000 images, you have something like 1,800 roughly. And that's something which you can easily run during a lecture. And so that's pretty useful for just testing things. But there is a real data set, a bigger one, which is much better. And the layers of, as we said last time, the layers contain typically a convolution part, which then contains a filter. And this convolution part has, in addition to the convolution itself, where we would typically have these filters with weights and parameters to be trained. Then we have a filter which inputs a reduced scaled image down to a smaller dimension. And then this is sent into a activation function, which is typically given by the rectified linear unit function. And then after that one, that produces an output which has been modulated. And that output is then sent in through a further dimensionality reduction, which is typically called pooling. And then you can continue like this. So you can reduce dimensionality further by new convolutional parts, new filtering, till you have produced a downsized set of images. You don't need to have only one image, but you can make many images which are downsized. And then through this filtering, you can then feed everything through a standard neural network, a fully connected one, because then you have reduced the dimensionality so that you can actually make the standard matrix vector multiplications. So just remember that let's say a matrix multiplication, if it's a square matrix, an n times n, that takes n cubed floating point operations. So even though mathematically it's simple to set up, computationally it becomes expensive if you have dense, large matrices. So normally you try to trim it down as much as possible, but the filtering can be done in many subsequent passes, because if you do just one filtering and you reduce too much the image, then you can actually lose a lot of information. So it's more reducing it stepwise, step size in steps, which is something you have to actually do case by case. So many of these filters are really tailored to the type of images which people have. If you look at a big data set like ImageNet, the filters there have obviously been set up in order to be able to deal with the recognition of images. And so the data set here, as we've seen last time, is now just simply us setting up the data set which is contained within scikit-learn, the other library, which doesn't have deep learning methods beyond a simple feed-forward neural network. And you would load the digits. That's the way you would do it. You have the inputs, and then you have the labels you want to reproduce, and these are given by the targets. So this is already set up for you. You don't need to stress with preparing the data. Sometimes that can be 80–90% of the work which is needed to be done. And then what we did was simply to plot it. So we have roughly 1800. This is 8 times 8, and we have one color channel. And when we import Keras, this is a way by which we can set up the basic interface with TensorFlow. So it's an API. And in this case, we need to introduce the input layer. We have a sequential network. It's going to be a dense. It can have more than one layer. We need to import the optimizers we want to use, and then also the regularizers. And the two categorical one is the class of output, which we want to deal with, which in this case has 10 categories or 10 classes. And the we split in train test. This is another feature included with the scikit-learn, which is always useful to use. So many people, instead of writing their own train test split code, they would typically use the one which follows scikit-learn. And here we set up the network. So this is a function which I have set up. It takes the input shape, defines the number of fields I want to have now when I'm going to set up the filter, the number of filters I want to have, the number of connected neurons, if I want to have a fully connected neural network, which follows after the convolutional stage. I have the categories, I have the parameters eta, the learning rates, and the regularization parameters. And here we have the convolution part where we define the type of filters, the input shape, and the activation function. And in this case, I just take the default, which is a max pooling. And this is defined here. And that does a 2x2, so it compares the 2x2 nearest neighbors. It flattens it out, which means it stretches out all information in terms of a vector, and that is fed in as input to a standard neural network where you set up the number of connected neurons, the type of activation functions, the type of regularizer. Here is the final layer, which is defined by these categories. And it has a softmax optimization function because we are dealing with 10 categories. And the same regularizer, it's going to have its own weights and its own biases. I specify stochastic gradient descent. You can make this more sophisticated. You can add this momentum. You can add the Adam optimizers, etc., etc. So these are just examples, and you would have to look up the way you plug in all the options you have. But the thing which is important for us is that you know which are the options. That's the most important part, the thing for us. And then we can use this as an interface to TensorFlow. And then we specify the type of cost function, which is now the cross entropy for the categories which we are looking at. And the metrics is now the accuracy, and we specify the optimizer. And here we also specify number of epochs, the batch sizes, and these are all parameters which we need to set up. The number of filters, and we're going to do 10 filters. the number of fields I want to have when I set up the filters. So the filters are going to be 3x3 filters, the number of connected neurons, the number of categories, and then the hyperparameters just as a primitive grid. And these are basically some of the parameters you can play around with. And what I did here was simply to run the code for the different learning rates and the different regularization parameters, lambda. And that produces an output, which when we compare that to the, so you would typically see in the output here, this is now for different learning rates and different hyperparameters, lambda. You see the kind of accuracy you get on the test data, which is 20% of the full data set. And which roughly then translates into something like 360 images. And then you can, I like to use this Seaborn package, which allows me then to display the accuracy. And you can see now that around this region here, where we have a lambda value of 10 to the minus 4 to 10 to the minus 3, and an eta value, the learning rate, from 10 to the minus 2 to 10 to the minus 3. You see now this is a kind of prediction which you make, which is roughly 99%. And according to humans, which have, I mean, training of humans, I mean, we are able to recognize roughly correctly 98%. So this model here does slightly better than a human. And you remember that with the standard neural network which we set up, we had in some cases, we reached a training accuracy and test accuracy of 1. So sometimes it could be that a convolution neural network for this specific data set does a worse job than a standard feed-forward neural network with just one hidden layer. So you would have to try it. But normally, if you have large images, you wouldn't grind them through a standard neural network. You would normally use a convolution neural network. So if somebody here is dealing with this type of problem in your PhD thesis, and I guess that Atle, you've been dealing with CNNs, haven't you? No, not okay. Then I may remember wrongly here. You're doing it, okay. So depending on what your thesis topic is about, I mean, you should feel free to change what I have suggested with one research which goes more in that direction. There is another data set. I just invite you to take a look at it. And this is the famous data set, which contains another 60,000 images. And in this case, we are using, these are 10 different classes. So I think there are different animals. And let me just see, I never remember what it looks like. So yeah, it's airplanes, automobiles, birds, cats, deers, and so on. I don't know why they always have to have trucks and cars and things like that. It's pretty boring. Okay. But this is something you could play around with. And by the way, there is a useful function in Keras, which is called model summary, which allows you to set out to see how many parameters you actually are tuning in the model here. And that's very useful when you have defined a network here. So like here, in this specific case, I'm actually doing 3 convolution stages. And I have 2 pooling stages here. And the activation function is Relo. So what I'm doing now, I'm just scaling down the images gradually. And then you can see for every step the kind of parameters you have on it. And at the end here, it flattens out the data you had from 3 convolutional stages. And then it runs everything through a dense layer here. So that's just another way of doing the calculations. And this is something you would have to try when you run the calculations. And you can see here, you can define Adam as an optimizer. So here we have something like a sparse categorical cross entropy, which is another type of loss function, which we discussed or briefly mentioned earlier. You can specify the number of epochs, etc., etc. I'm not going to run through this one because it takes a little bit more time here. So what I wanted to begin with is actually, unless you have any questions about CNNs and whether that relates to your research or not. as I said, these projects are very flexible in the sense that you should feel free to define the kind of content of the projects. So what I wanted to say, and this goes back to the project number 2, when it comes to the differential equations, because you can feel, or you can rewrite a differential equations in terms of a recurrent neural network. And I'm going to show you the basic steps here. But first, I wanted to give you some kind of more overarching views on recurrent neural networks and what they can be used for. So we have typically been looking at CNNs, or normal feed-forward neural networks, and the output or the activations, they typically flow in one direction from the input layer to the output layer. So a recurrent neural network looks very much like a feed-forward neural network, except that it can have connections which point backward. And you can get at every stage, suppose at every hidden layer you can have an external input and you can produce an output. So just think of a differential equation where you feed in to the differential equation solver the previous position, and then you obtain a new position. Or think of you having a system under the influence of an external force, and then that force feeds in as an input to your system, and it produces an output at a given time. And then you move to the next time, to the next time, to the next time. So you could make a measurement where you have an external input to the system at every time step, and you have an output at every time step. And now you're going to train the data with these time-dependent outputs. So I'm very much biased towards solution of differential equations. That's what I normally do. But normally RNNs have been used a lot in natural language processing. So that's many of the examples you will see in machine learning courses, they are more tailored to these type of examples. So I'm going to tailor it more to natural science problems like solving differential equations. So if you look at this, so what we're actually doing is to apply machine learning to sequences. And you want often to turn an input sequence into an output sequence that lives in a different domain. So you could think of turning a sequence of sound pressures into a sequence of word identities. And we're going to look at that, but I wanted to give you a simple example first. So in this simple example, what I'm doing now is simply to define a function, sine. And I'm going to do this, as you can see here, in 1,000 time steps. I'm going to have a time up to 800, the 800th time step, which is going to be my training data. And then I'm going to train a recurrent neural network on the first 800 points. And then I'm going to use the result to predict the next 200. You see what I want to do? So this is the basic thing I'm going to set up. So, and you see now the function is, since I'm a person, according to my wife, totally void of fantasy. I like harmonic functions like sine and cosine. So lack of fantasy and the wish to be harmonic gives a sine here, or a cosine. Later we can add some noise, which is actually closer to my life. And what I'm setting up now is I'm just plotting the results. And then I'm setting up a model here. And in this case, I'm just using a simple recurrent neural networks. It's going to have 32 units. I'm going to explain that just shortly what it means. It's going to have an activation function, which is the ReLU. It's going to have dense layers. I'm going to have 8 dense layers with activation function ReLU. And it's going to produce a mean square error. And the optimizer is the root mean square propagation. So this is just the way I'm going to define the model. So it's a sequential one. It's a simple recurrent neural networks, and we are coming back to more complicated ones next week. And then I'm going to set up my data I want to train, and also the data I want to predict. So I have a train prediction, test prediction, and here I just look at the train X and test X, which I'm going to set up here. So what you will see now is something which looks like this if I have the random noise, but I'm going to rerun this now. So this is what, if I have some random noise, this is the way. Let me just squeeze this down a little bit. So the data looks more like, sometimes I have some problems in increasing these, something with my pointers here. Okay, but this will be roughly the sine function with noise, but I'm going to rerun this now with without the noise. And then we're going to look at the kind of prediction which we can make. So this is a standard harmonic function. And then you can see now the parameters which we are setting up. And so this gives you the number of parameters we want to train. And now it's just running through it here with the training. So it runs through a given number of epochs. This is the loss function, which I'm training. And you see now the loss function is pretty small.
What loss did you use?
Say again?
What loss?
So this is just the root mean square. So because I'm just, in this case, I have a function like the sine. So I'm training for the 800 first points here. And the you can now see the, when we run through this, you can now see the line, the blue line is the one which I'm produced, and then the other one is the one which I'm predicting. And you can see now that the till 800, that's where I'm actually training my data. And beyond 800, you can see the type of prediction which I make. And that's actually, it looks pretty good on the graph here. So this is a typical example of how you could use a recurrent neural network. Now, what I was thinking of is that we can, and that's something I want to discuss a little bit next time, is how we can actually set up this for the solution of differential equations, the same data set which we have in the project, but where we actually use a fully connected feed-forward neural network. So, and you typically see the kind of loss which you get here on the, I think that's the loss which we get on the predicted results. Now that's a train score. So I didn't actually plot the test score here. I should have done that as well. I forgot to do that. Okay, so what I wanted to do now, before we go back to these different slides here, is to say a little bit about the kind of motivation and how we can set up a recurrent neural network. So I'm going to switch over to the whiteboard, if it's okay with everybody. I'm going to use that one. Okay. So what we're going to say now, after we looked at this kind of more overarching ideas behind the recurrent neural network, is that this RNN is a kind of network, or neural network, which is specialized for processing sequences of values. So the RNN, if we want to frame them in a specific sentence, they are specialized. And that's why they've been used for natural language processing. They are specialized for processing sequences. Of data. And it can be used on data with unknown length. That's another thing which is worth thinking of. Remember now that the standard neural network is normally used for, on very, very homogeneous data. So the data set can be of unknown length. So each stage, if we now want to be a little bit more detailed, so each stage in an RNN contains the following: new input. So you can think of each stage as a new time step if you look at this as a time series. So is any one of you going to deal with time series in your PhDs? Okay. The differential equations, or the solutions of differential equations, can be viewed as time series. But you could have data which are given by measurements over time. So if you're measuring stress for people with diabetes, for instance, you could then measure the stress response every, let's say, 10 minutes and see if a patient with diabetes reacts differently with respect to a patient who doesn't have diabetes, just to give you an example. That would be a time series. So you would have new input at every stage, and you can manipulate the state, which you have. And we're going to see how we can do that. So it can manipulate that state in order to produce an output. So you are feeding in some kind of input, and then your machinery here produces an output at each stage or each time step. It's going to reuse weights in the next stage. And it gives a new output at each stage. So that means that every kind of stage or instance, we produce a new output. So you can think of an RNN as a series of measurements. So think of an RNN as a series of measurements. That's the kind of way I like to think of it, of measurements. And let's look at a simple example. And the simple example is one which we also plugged into the project. And that was the Newtonian equation of motion. So we would have something like an m over d of x, the second derivative of x, which is the acceleration. We could have some damping factor, which is proportional to the velocity, the first derivative of position. We could have an x of t here, and then we could have an external applied force, F of t. And the system is defined, the solution is defined by the initial conditions. So you could now think of having initial conditions here. And that is some x0, which is at x of time t0, which normally is set to 0. And you would have a v0, which is just v of t0. So in order to solve this system, because you have a second derivative and a first derivative, you need two initial conditions to solve the problem. So we are typically, the way you would solve this type of equation is to rewrite it as two coupled first order differential equations. So the standard way is to rewrite as two coupled ordinary differential equations. So ODE stands for ordinary differential equations. And that means that you would have a V of t, which is given by dx dt. And then finally, you would have an equation for the acceleration here of dv. So the acceleration is a derivative with respect to time or the velocity. We assume that masses don't change. We also assume that this constant eta is time independent. And then we have plus the velocity plus x is equal to this force, applied force. And if you discretize, which is the standard way by doing this, and you take the simplest possible approach, Euler's method, which is just a manipulation of Taylor expansions around the point, then we have a discrete time, t of I, which would typically be given by t0 plus some I times delta t, a time step. And this I goes from 0, 1, up to the final point n. And this delta t would then be given by final time, tn, minus initial time divided by the number of points. And then we have x goes over to x of I, and v goes over to v of I here. So these are just standard setups. And if you use Euler's method, Euler's forward stepping, simplest possible method we can implement, then we should in principle have an approximation, but we're just going to put an equality here. So this is going to be x of I plus delta t times v of I. And then we would have the same equation for the velocity. And we have v of I plus 1 is equal to v of I plus delta t multiplied with the acceleration a of I. And we have an expression for the acceleration, which is actually given by the term which you see here. So this is the acceleration. So if I move this term, that term over to the right-hand side and divide by mass, then I have the acceleration, which is what you would plug in here then. Now, if you now look at the equations here, suppose now that we are interested in the equation for the velocity only. So that means that this dv dt, which is the acceleration, a, this is going over to an a of I, that's going to be equal to this f of I divided by mass minus this parameter eta divided by mass multiplied with v of I, and then it contains a new parameter minus 1 divided by m times x of I. So that's the acceleration. And that means that I can now rewrite. So let's now just call this for a of I. So it means that my v of I plus 1, the next time step, is a v of I plus a delta t. And it's going to depend on v of I, as you can see here. It's going to depend on this x of I, and it's going to depend on time, and also this force F. So everything which you see in here, so let me just skip the explicit time dependence and just write it like x of I and f of I here. So, and this is going to be a function which I'm going to rewrite as a function f. So let me, I just forgot to put that one in here. So this is plus a delta t multiplied with a function f, and where that function is actually given now by, so this function f is the same as what we had up here. That sound okay? So I'm just writing this side here, this acceleration, in terms of a function which now depends on the velocity, the position, and the specific force. And I have suppressed the time dependency. So if I now rewrite this, I could write it in a more compact form. So as you can see, this is a kind of repetitive operation where we just keep repeating. So I could rewrite this in a more compact form in terms of a new function, which I'm going to call g, which now will depend on this function f of v of I, x of I, of f of I. And now we have to be, or let me just rewrite it before we take a break. Let me just, I can rewrite it as follows. So I can, because the velocity, the previous velocity here, so it's f actually, and it's again f as a function of v of I minus 1, x of I minus 1, and then I have f of I minus 1, and then I have the new value of x of I and the new value of f of I. So if you now look at what I've done here, I took this v of I, which actually, if you look at the expression here, is given by the same function f, but now evaluated at v of I minus 1, x of I minus 1, and f of I minus 1. Is everybody willing to buy that? Okay. So what we have is a kind of dynamical system which is driven by an external force. So you could actually set this up diagrammatically now and illustrate this in terms of an external input, which is now the force which is fed in, this position x of I, and that produces an output at every time step or every stage. But I see I'm running a little bit over time, and I suggest we just take a small break. Is that okay with everybody? Just 15 minutes to stretch legs. And then I'm gonna stop the recording here, or pause the recording. And then we take a small break. Okay, so the kind of thing we were doing before the break was to look at the differential equation as a stepping stone towards the basic setup of a recurrent neural network, so that you can see the basic elements, which then enter the setup of an RNN. So the thing which we end up with can do here, if we now suppose we, when we looked at this differential equation, which is a standard Newtonian equation with a damping factor and an external applied force, with initial conditions, we split it in two coupled ordinary differential equations. And then we can rewrite, let's say, the part which depends on velocity in terms of a more compact way of rewriting it. So we have the velocity at the next time step, which is now given by some kind of input here. And then this is the input from the previous value, which is the previous velocity. And then I have the previous position and the previous force, which is applied to the system. So if you now look at what we have here, what you could say now is that this piece which you see here, which is our v of I, we could then, or the part, this would be actually not v of I, sorry, but this is actually this function f of I. So which is this piece which we had here. We could illustrate this in a graphical way. So you could now think in the following way of presenting the results which we have in a graphical representation. And this is the way we're going to set up things pretty soon. You could now think of u starting with an initial velocity, v0, and this propagates through the system, and it reaches a specific velocity here, and then it feeds in to this function, the previous values, this f of I. So this f of I receives an input. So this is what we compute now, this f of I from the previous step, and it receives an input, f of I and x of I. And then it produces an observation. And this will be our v of I plus 1. So you can now think of, if you go back to this expression which you see here, so you have a v of I plus 1, which depends on the previous value v of I, which is now included in this determination here, plus this delta t. And this set which we have, so this v of I, if I look at v of I plus 1, could now be encoded in terms of an additional function here, which now depends on a previous time result. Now this v of I plus 1 is now also fed into the next step, which then computes f of I plus 1, and this receives as input f of I plus 1, and I have my x of I plus 1. It gives an output v of I plus 2 here. We had plus 1 before. And so this gives me a V of I plus 2 here, which then is fed into all the next ones till the final time. So we get something like an F of tau here, and then it produces a V final. So this is our final time, and that has an input F of tau, which is the final time, and X of tau here. So this is something, what you see here is an input from an external probe. So you could make this a little bit more general, and you can now try to replace this one, not with the simple model which we have, but with something else. So you could now think of this as starting to represent the basics of such a network. So what you could think of now is to make it more general. So by the way, you could think of what you have here as either the solution of a differential equation at a new time step. And this is in a way exactly what you're doing now in the project. The differential equations we have, we're actually producing the solution at a time I, and then we step it forward at a time I plus 1. And what we are doing then in a standard feed-forward neural network is that we would take the value which you see here, this V of I, and use that as an input value to a neural network. And then we would use this as the output. And then we are letting the neural network figure out this piece here. So that's the first step in the project, where we just use a standard neural network. So for every time step, we have a previous value and a new value. So that becomes input, and this becomes the output to a standard feed-forward neural network. So that's the first stage of project number 2. Then the next stage is to, for example, replace the standard feed-forward neural network with a recurrent neural network. And in that case, you could now think of you having these as observations, and then you have the input values. And at each time step, there is an input and an output. And then you want the network, this recurrent neural network, to actually train this. And then you could train it up to, let's say, this time here. And then you could use the network you have trained to make a prediction for the next time steps. So that's one possible way of applying these recurrent neural networks. So that means that you could use a differential equation solver to make the solutions for some time steps and train a network, like we did with the sine function as a simple example before the break. And then we made a training for the first 800 points, and then the trained model was then used to make a prediction for the next 200 points. So think now of these as a kind of observations, which are then used to train a model. So let's try to make this a little bit more general now. So what I'm going to do now is to assume that this V of I plus 1 is now replaced by a more general function, some function S of I plus 1. And this S of I is now going to be a function which I'm going to replace with a hidden layer. That's why I'm going to put an H on it. And it will depend on a previous value, S of I. It's going to depend on an input value. So now I'm going to reduce my input from X of I and F of I to just X of I. It's going to contain some inputs, and then it's going to have some parameters. So theta are now the parameters. So these are my parameters. This is now going to be an H of I. So these are the parameters which we want to train. These X of I's are then the external probes or external inputs. And the S of I would be the input from the previous network, from the previous hidden layer. Let me just quickly say something about a graphical representation, which is very convenient now, graphical. So what you could have is something like an operation. If you now look at some X, this is some input, and some Y, some input, and you're performing a multiplication, you would often see this with an X here, and then you have a Z. So this is the same as is to be read as Z is equal X times Y. So that's a multiplication. If you then take a function, suppose now we are looking at a function Y, which receives an input from a function F. So this could be, let's say, a vector X and a weight matrix W plus the biases. So this could be our activation function for a node in a neural network. So this would be something like an F of Z. In this case, the way you would represent that one would be something like this. So you have an X, and then you have a W. And this feeds in to produce, so we have a dotted value here. So we have a dot product. And then I'm producing now a variable Z, which then feeds in to this function F, but it receives also a variable B. And this is plus now. And that produces an output Y. So this is the way you could now represent a process like that one. And you could think of this F, this could, for instance, be a ReLU function, as an example. So you are producing an input to a ReLU function in a standard feed-forward neural network. What you're also going to see is something like this. So I'm producing now some input X into a function. So I have an X, which is now fed into a function H here, X. And this is now written like this. And then there's a black box here, which does the black magic for us. So we can open this up. And you will often see that kind of representation here as some kind of shorthand representation, where you could think of these H's as you having some H at a given time. And I'm going to put just dots in here. So this is a time, long time ago. This feeds into a new H. So an H of T here, which then gets an input X of T. And this feeds into the next one. And there's a function which is evaluated, a function F, for instance. And this feeds into an H of T plus 1. It has an input, X of T plus 1. And this continues till a final time, which I just indicated with these dotted circles, where I have an H at a given final time here. And that has also its own input. So you will often see things written in a compact way like that. That means that when we now are going to set up our first feed or neural network, a recurrent neural network, the way we can think of this now is the following. So if you look at that function S, which I put up here, this specific function here, I could now use this one to set up a network, a general one. And you could think of having some S0, some initial value. And after some time, it feeds into some s of I minus 1. There is some input x of I minus 1. And this continues to some s of I. And then it has an x of I. And this goes on. So this s of I is now given by this function h. So s of I is given by a specific function. By a specific function. Which we called h of I. So that means that what we could replace this with now is some initialized neural network H, or hidden layer. This feeds in to layer 1, H1 here. That receives an input X of 1, and it produces an output Y of 1. This information is then fed into here. So I have an H of 2. It has an input X of 2. It produces an output Y of 2. Continues like this to the final time. And this is an H of 3 and Y of 3. And this just continues. And it's normal to just rewrite this as follows. So we have a box here, which we call an RNN. It has an input X. It produces an output Y. And then we have the hidden states here. So these are the so-called hidden states because we don't measure their properties. So the only thing which we have as information from each stage here is Xi and Y of I. So these are the quantities which we measure. And then some black magic takes place in here. Okay? So these are just graphical illustrations of a so-called recurrent neural network. Now, if we now are setting this up and we want to be a little bit more detailed than this, we could now draw a graph. And let me just get a good, nice drawing here. So the typical way you would set this up now is as follows. So you have some initial stage. And this feeds into a stage h of t minus 1. This is now used to produce a modulated output. So it produces, well, let me just bring in some more space. I need a little bit more space here. I'm just gonna go down a little bit. And maybe I'm gonna tilt my page, see if that works better. Now let me just keep it like this. So we have an initial stage that feeds in to this function h of t minus 1. This receives an input x of t. It modulates everything. Now, I actually need a little bit more space here because my drawing is not the best. That was bad planning from my side. Eh? I should have used the figures which I have, but I normally like to write them down. So we have a hidden layer, and that receives an input, x of t. This produces an output because it sends it into a function, f of t minus 1. And that produces an output. So f of t minus 1 could be our ReLU function, just to give you an example. So there is a hidden layer here, which now sets up the connections between the previous layers, which we had here. It receives that as input. and then it receives an input from an external probe. It feeds this into a function, and what it feeds into a function produces an output. So it produces now an output, which is our model output, which is t minus 1. Now, this is again sent into a loss function or cost function at t minus 1. And these results are compared with the output, which we want to reproduce. So there's a y of t minus 1. So this is our model. Now, this result is then used to produce a new input to a new hidden layer, h of t here, which then takes into account, sorry, this should be t minus 1, and I have an x of t here. This is modulated by some kind of activation function, f of t. It produces a new model result, y of t tilde. This goes into a cost function, a c of t, and there it's compared with y of t. And then you see now that you can continue this till the final time t plus 1. And then you have an external probe here, x of t plus 1. This is modulated at a t minus 1 plus 1. It produces a y of t plus 1. And then this goes into a new cost function, ct minus 1. And this goes into y of t plus, as an input y of t plus 1. So that would be the basic structure of such a neural network. And this just continues till final time. I'm just putting dots here. So this will be the final time here. So if you now want to decode this, the way we can actually rewrite it. So let's just try to rewrite this one. And what I'm going to do now in the rewriting, I'm going to skip this function f just for simplicity. So I'm going to skip this function f for simplicity. So just think of this as now being absorbed into this hidden layer. So this is now absorbed by h of t. Now we can start setting up the weights which we need to train, or the parameters which we need to train. So what I'm going to have is now some h at a given time, and I just put dots in here. That feeds in to my h at a time t minus 1. It gets this input from x of t minus 1. Now, in my case, these hidden layers are connected. So these are the parameters which link the previous hidden layer with a new one. Then there is a new connection between this specific input and the hidden layer. So that gives me now parameters which need to be trained. So this contains parameters to train. And then I'm going to link this with the output. So I'm just going to write this as a y of t minus 1 tilde. That feeds into the cost function c of t minus 1. They are normally always equal for each time step. And that receives an input t minus 1, or rather the output. And that means that there are going to be parameters which link this hidden layer with the output layer of the model. So this is the model output. And that means that we have further parameters which we need to train here. So this continues. So till the next layer. So we're going to have a new weight matrix. And sometimes we often use the same weights. So typically what is very common in such a network is that you use the same weights for the inputs. That means this axis, which we have here. So it's common to reuse these weights for the input, and then simply train on this one and that one. So this is a network which is a network which now has a memory of all the previous results. So this goes up to, so let me just draw it up like this. So this has a y tilde of t, and then it goes to a c t, and that receives a y of t. And then I have a new x here of t, and this has a weight, again, which needs to be trained. And I have the weights here, which also need to be trained. And this again just continues till the final time, to final time. Now, if you look at this network here, and you're thinking of a efficient computation, so let me just mark the different things which we have here. So these are parts of the model. Same here, same here. So the kind of data which we feed in and get out are the y's and the x's. And that has information from previous time steps. So what you could say now is this is a memory model in the sense that it keeps information about the training from the previous time step. So in a certain sense, it mimics what we did with the differential equation. So in the differential equation, you could now think, if we go back to that from the slide which we had up here, if you look at this one, this is what actually keeps the memory of the previous time steps. And so what the neural network is actually doing, or the recurrent neural network, is to try to build up a memory by linking the different time steps. So here we are linking the next time step with the previous one, with the value which we have here, and these parameters which enter here. And the same thing happens when we now are setting up this specific network here. So we have an information from the previous layer. This is something which only connects within a specific layer. And you could now assume that what connects this output from the model and the input to the hidden layer here is something which doesn't change over time. So you could say that, okay, in order to save CPU cycles, I only train on W's and I reuse these weights and these weights. Or you could just say that my input is of the same character all the time, and I don't change these weights, but I rather train these ones and the W's. So you can actually, in order to save time, there are many small tricks which you can do if you want to save cycles. And that is to, for instance, just reuse the same weights over and over again, and then just simply train in one of these instances and then just use for the rest. Alternatively, you train everything in a sequential way. Now, there's one big drawback with this. It's actually a very good model, but what kind of drawback strikes you if you think of computational efficiency, and in particular high performance computing? If you look at this model, it's extremely sequential. So this means that a recurrent neural network is the way this is set up. This is one of the ways of doing it, is non-parallelizable, because it depends on you having computed things at this time step, then this feeds into the next time step, and so on and so on. Now, one thing which you also have as a flexibility here is that these hidden layers, they don't need to be shallow. So you can actually have a deep neural network inside every hidden layer here. So you could have a convolutional neural network, you could have a standard feed-forward neural network inside here. And that could be deep or it could be shallow. So you're not limited to just one type of setup here. Now, there's one thing which is a drawback here. So the way it actually works is something which is when you train the parameters, the basic algorithm is called backward or back propagation through time. So this network which you see here is normally trained by back propagation through time. So that means that you perform a feed-forward process. You initialize all the weights and the biases which you have here. And as you can see, you need to set weights here, and weights here, and biases as well. So at the end, you have lots of training parameters. So you would start training the network with a feed-forward pass, and then you perform a back propagation through time. So that means that the back propagation would enter every stage which you have here. And that's how you train the parameters of the network. And then you go back and forth till you're satisfied with the training of the data. And you could decide then to train, for instance, the first half of the points you have, and then use the network to make a prediction for the remaining points. So if you have typically a harmonic solution, a sine or cosine or things like that, then this is normally an extremely good approach. So if you have something which repeats periodically, then you could actually train with much less points and actually make a good prediction, instead of solving a differential equation at every time step. So it's in a way, it's a way to reduce the dimensionality then in the solution of a differential equation. Okay, so this type of network is actually a sequential one, as we said. So we cannot reduce the operations by parallelizing, since it's an extremely sequential process. And this way to train a network is normally called, as I said, back propagation through time. It is very powerful. It gives great predictions, but it is expensive to train. It's time consuming, and it requires a lot of memory. So that's clearly one of the drawbacks with this type of recurrent neural networks. You can reduce this kind of complexity by, instead of setting up a fully connected networks from one time step to the next one, you can reduce the complexity by a slightly different design. So this network, as we said, is difficult to train, or impossible. It's very sequential. So it's impossible. I'd say it's impossible. So it's impossible to parallelize. It becomes CPU expensive, CPU and memory expensive, but it gives normally excellent results on time series. So one typical network which can reduce the CPU expenditure and also the memory expenditure is to avoid this connection. So a slightly different architecture, slightly different architecture is the following. So what you would have now, if you now set up the H at t minus 1, this receives an input at x t minus 1. This receives now not the information from the hidden layer, but actually from the output layer. So this feeds in here. This produces an output y of t minus 1 tilde, and that goes into the cost function c, and then with the y of t minus 1. This then feeds in, instead of the hidden layer being connected to the next hidden layer. So that means that the only thing we would have to set up then would be the weights from the input to the hidden layer, and then the weights from the hidden layers to the output layer. So just think of what you have here as a standard feed-forward neural network, where you have an input layer, you have a hidden layer, and then you have an output layer here. And that output feeds into the cost function, and that's where you compare with the targets you want to reproduce. So that means that this would now feed into h of t, and this has an input again, an external probe, which feeds in something to the network. This produces an output, y tilde, which then goes into the cost function, c of t, and is compared with a target, y of t. And then this just continues and feeds into the next one, h of t plus 1. And then in this case, I have an x of t. And I have parameters to train, v. I have my u. So I'm just going to put up this one and just put dots here. So this just goes on to the final time. And in our case here, what we have are the parameters to train here, 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 and here. So those are the parameters which we need to train. You can also reuse some of the parameters. It's pretty common to actually take the parameters from the external probe and just keep them fixed throughout the network. And then the only thing you would train would be the parameter inside the hidden layer. The thing which is distinguished itself here from what you've seen before is that in this specific model here, you don't keep track of the memory from the previous stages. So that means that this is a so-called memory-less model. The previous one is a memory-heavy model because it keeps information from the hidden layers from the previous time step to the next time step. Whereas this model here does not have that information. So it's easier to train, and it can be trained in parallel. But it's normally it's a model which gives, how to say, less. I mean, the quality of the results is normally inferior to what you have if you have a standard recurrent neural network with backpropagation through time. I see I'm running a little bit over time here. We'll take a small break again. Just stretch legs again, if that's okay with everybody. So to summarize this specific approach, this kind of network approach which we have here lacks the hidden-to-hidden connection, which comes through with the previous model where we had a connection between the different hidden layers. And it cuts down the number of weights we need to train. It's, from a computational point of view, easier to train. However, it gives results which often are not as good as the previous one. So there's always this kind of trade-off between accuracy you want to have and the number of floating point operations which you're willing to spend on a given calculation. And this all training steps which you have here, they can actually be decoupled in time, and you can thus parallelize the calculations. Now, there's one thing I just wanted to do before we move on to the final topic with recurrent neural networks. And I'm going to sneak in another small thing next week, but then I thought that next week we could just focus on the projects, and the same with the week thereafter, before we begin with Bayesian statistics and Gaussian processes. So I just wanted to switch to the, where are I now? I'm going to switch to the slides. So if we want to summarize what we have, if we look at this kind of recurrent neural networks, let me just bring it up. So you would then have a typical neural network, the way we are used to have it. We would now have this typical feed-forward pass and the backward propagation. And in the recurrent neural network, what we have is also an external input. We produce an output, and then we compare that one with the target. And then we have the recurrent edge here, which means that we have something when we unfold it, as we discussed before the break, you will then have something which looks like this. Can you see this image as well? And this is something which there's actually, if you want to look at a textbook which has a good mix between algorithms and explanations, there's a textbook by this guy called Sebastian Raschka. And I've actually borrowed the images from that textbook, as you can see. And in this case, what you see now is you're unfolding it. You have the external probe, which feeds into the hidden layer, and you have a target value you want to reproduce. This feeds into this one, and then it continues to the final layer. And you can have a single layer recurrent neural network, or you can have a multi-layer recurrent neural network. And you could also have filtering inside here. So you could actually do a convolutional neural network inside a given hidden layer for a recurrent neural network. So if that is something you need to do, a kind of dimensionality reduction at each stage here, that could be something which is worth trying, looking at. And typically, each hidden units here receives actually 2 inputs. So you would have an input from the previous one, and then you have an input from the external probe, as you can see here, just to summarize what we've gone through. And when you unfold it and you have a multi-layer, then clearly you would have more connections between the different. But what you would do then is typically that the last one here would then feed, because that would be the last layer in a sequential model at one time step, and that feeds into the next one, which also gets an input. It can get an input depending on how you set it up. You can either let this one feed in, or you can let all the networks feed in here. So this depends on the architecture you want to develop. That just gives you more parameters to train. So you could think of this one producing the final output and just use these weights as input to the next layer. There are different types of this kind of sequence modeling tasks. So you can have many to one, you can have one to many to many, etc., etc. So there are several ways by which you can set up your neural network here. And you need to specify, the way it's normally done is to specify initial states of all the hidden and output units. And it's normally better to treat initial state as learned parameters. And you can learn them in the same way as you learn the weights. And you start off normally with an initial random guess for the initial states. And at the end of each training sequence, you backpropagate through time all the way to the initial state to get the gradient of the error function with respect to each initial state. And then you adjust the initial states by following the negative gradient. So you can actually specify these units, these inputs in many ways. And in our case, we are dealing with this differential equation. And that means that the input would typically be the value of the differential equation as initial value parameters. And there are many ways by which you can do this. And there are also many ways you can specify the targets. So I just invite you to take a look at this. And these are things which are taken from Goodfellow's text. So depending on the type of application you have, there are tons of different ways by which you can do that. I just wanted to show you a little bit the kind of parameters we end up having to train. So let me just find that image. So the typical stage now is that you would have weights which would connect the neural network to neural network, a hidden layer to hidden layer. You would have these weights, and you would have the weights which connect the external probe, which feeds into the network. So these are the type of parameters which you would need to train in the neural network. And so that means that you would have input types of this style here. You would have a matrix here, which multiplies with the input, like you would have with a standard feed-forward neural network. And then you have the hidden layers to the hidden layers here, and that contains information from the previous value. You would have some biases. And then this h of t, which you have, which is being produced from here, this produces an h of t. This is given by the output from this hidden layer into an activation function, which then produces my output at each stage here. So that would now contain this h of t, and then these biases, and that produces a final output via activation function here. So in addition to the weights, you also have the biases. And the overall loss is normally, can be, so you can actually train the network at each time step. Alternatively, you can take the overall loss, can be computed as a sum over all time steps. So there are two different ways which are normally used, is that you collect the difference between the output and the target value at each time step. You collect them and you define a total cost function, loss function, and you use that one to train the network. Alternatively, you can train the loss function at each time step. The common procedure is actually to take the total final one and train that one. That's a standard procedure which is being used. And then you would have back propagation through time here, which is a standard approximation which is being used. And that means using the chain rule and just back propagate and train all the weights and biases by going backward. But your total loss function would then be the sum over all of them. And the reason why I'm setting this up now is that this algorithm has a problem which leads to a recipe which I really dislike strongly, which is called gradient clipping. Because you see now, there's one thing which can happen if you're performing these multiplications again and again. And that is, since every layer you have, you produce gradients, and they're being multiplied with each other. And that can give you gradients which really explode. So let's just see that and try to convince ourselves why this is a problem. So the way it's normally cured is actually by saying that if my gradient is larger than a specific value, I just set it back to a smaller value. And then I continue happily and without any worries. And this is one of the problems with this method, is that you can actually get gradients which become very large. So let's go back to the Jupyter notebook. No, not the Jupyter notebook, but to the notebook here, to the whiteboard, and just show how this can happen. Oops, I didn't like that. Let me try this though. Yeah, now it come back. I don't know why it came out as a black screen. I don't know. Yeah, we can infer that on black magic. So now comes one of the challenges with the RNN, and that's normally called the challenges which are related to long-term dependencies. Because what we are doing with the standard back propagation through time is that we actually depend on the gradients at different time steps. So that means that I can bake into the calculation of the gradients time dependencies which reside in times far ahead in time. So in RNNs, we store the weights and the biases for each time step. And they involve the calculations of essentially the same function multiple times. So when we are running these calculations, what we typically do now is that we have an h of t, which is typically given by a weight matrix multiplied with h of t minus 1. So this is essentially what we are doing. So I'm just trying to simplify things now. And what you could think of, if you do this over many, many times, you could now think of this h of t as something which is being repeated many times. And this is now multiplied with the initial time here. So this would be u. So let's assume now that we are reusing the same weights again and again and again. So we have the same weights. So we have W times W times H0. And this is done T times. So this is basically what we call the power method. So one thing we could do now to illustrate the kind of problem we end up with is to look at this function, this matrix W, and we could assume that this matrix can be diagonalized. So assume now, just to illustrate the problem which we have, assume W is a matrix which we can diagonalize. So that means that W can be rewritten in terms of a transformation where U is an orthogonal or unitary matrix times U transposed, and where we have obviously that U of T times U is equal to U times U of T, and that's equal to the identity matrix. So we assume that. So we have eigenpairs of W R lambda I, and then it has eigenvectors Wi. So we're assuming now that this is an orthogonal basis because the matrix is diagonalizable. And that means that what we could do now is that we could expand this H0 in this basis. So I would now have a basis with a given number of eigenvectors, and I have this alpha y and Wi. So remember that if you have a basis from a diagonalizable matrix, you can think of this as a basis you can use to expand another function in. Whether that's a good expansion or not is up to you to discuss, right? So that means that if you look at the action of W times H0, that is the same as the sum over I, and then you have alpha y, and then obviously lambda y because I'm acting. So W times Wi is given by lambda I times Wi. So this is simply multiplied with Wi here. Okay? So if I do this repeatedly, if I now assume that I have the same weights throughout this operation, and the same weights link one hidden layer with the next one. So what I have then is that my H of T, so this is just a simplification of what we are doing now, is given by this sum, this repeated operations with Wt on this alpha I times Wi. This is simply going to be given by lambda I of lambda I to the power of T of alpha I times Wi here. So the thing is, you see quickly now that this product can easily explode, or it can be contained within some value. So what you could assume now is that we have ordered the eigenvalues. Assume now that lambda 0 is larger than lambda 1, larger than lambda 2, and then we have larger than the final eigenvalue of some lambda of n. And that means that this H of T then, so that shouldn't be there, H of T is then going to be proportional with the largest eigenvalue times W0 times alpha 0. And this typically leads to either a vanishing gradient or exploding gradient, depending on the value of lambda 0. So depending on the value of lambda 0, we can get what we call vanishing gradients or exploding gradients. So this is the extreme case, but you can actually generalize this to weights which are different from time step to time step. So you will then have a product of different eigenvalues here. And the if you then want to avoid this kind of problem, is that you could then you need to think then of how you want to treat this kind of particular exploding gradients. So to avoid exploding gradients, there's a trick. And you see also that if this lambda 0 is less than 1, then this value is going to die off. So you will actually get vanishing gradients then. And that's another problem which people try to account for. But the exploding gradient is often a more serious problem. A simple trick to avoid exploding gradient, a simple trick which is being used, is to take the gradient, is to clip. I'm just going to write it like this, clip the gradient. This is called gradient clipping. And the recipe is pretty simple. So you have a gradient G, and I put a vector on top of it. And the test is very simple to implement. If G, the norm of the gradient, is larger than a specific epsilon which you have chosen, then you would change the gradient. So you would then take epsilon divided by G, the norm 2, and multiply with G here. And this is a typical way by which you would clip the gradients. And this is often implemented in this kind of a recurrent neural network with a back propagation through time here. So the vanishing gradient is normally less of a problem because in contrast to a feed-forward neural network, the recurrent neural networks, they typically get new inputs all the time. So that means that the weights get adjusted to that. And it means that the vanishing gradient is something which very seldom occurs in recurrent neural networks. And it's not seen as a problem. But the big problem is actually that of exploding gradients. And the standard trick which is being used is actually this one. It doesn't look very satisfactory, but this is normally the kind of standard trick. The challenge is to learn the long-range dependencies, which can allow you to make extrapolations and predictions of results ahead of the time domain, which you typically have. And the training is normally done using this backpropagation and the gradient descent algorithm, which we have discussed in many, many other occasions. So these kind of gradient descent methods with backpropagation are the standard recipes which are actually being used. And one problem you also see is that to calculate the gradients, you need to keep track of the values of the weights. So if you go back to the training of neural networks with the RNNs, we need now to, in order to perform the backpropagation properly, where you have the derivatives of the cost function backpropagated through every time step, that means that you need to store the values of all these matrices. And that requires a lot of memory. So that's one of the other drawbacks of convolutional neural networks. And the different types of cost functions, they can also leave, I mean, they are normally the different cost functions which you get. Like we put the cost functions here for every time step. These are normally collected just in one final cost function. And that's the one whose derivative is taken at the final time. And then you backpropagate with that final cost function. And that normally reduces a little bit of the memory requirements. And it also gives faster parameter updates. So the drawback with accumulating all the cost functions into one is clearly that it is not able to capture the kind of long time dependencies. Okay, so I am going to actually stop here a little bit today. And I thought we could use the rest of the time to discuss projects. And next time, I wanted just to wrap up quickly about this long short-term recurrent neural networks. That's one way of implementing the training of the different weights and biases. And then if I get time, or if I have the energy to do so, I want to say something about autoencoders. If not, we are just going to work with the project. And Atle, whom you met in the beginning, he's going to hang around and he's going to discuss with you. So that means that next time and the time thereafter, it's more project work and discussions. So I'm going to stop the recording here.